So welcome on the next lecture. We started to discuss manifold last times, and there are several points to be said there. So first, I remember you that we defined topics like immersion and embedding. Immersion is a mapping from a manifold M to a manifold N, which can be defined in several ways, but what I expressed here, that if you have this formula for a mapping, you can compute a Jacobi matrix and this Jacobi matrix has some rank. It is in general not square matrix because the number of indices of A is maybe different than the number of indices I. So this non-square matrix has some rank, and this rank, if this rank is maximum rank, then it is called immersion. And if you have a look to the book, you will see that there is also another definition which is based on some existence of some special coordinates. It is also useful formulation of this concept. But now I just say about this definition, that this should be maximum. What it means, it is not so easy to discover what exactly it says, but actually it is something that if it is smaller dimensional, this one is that M is smaller than N, then we can draw a picture, something like that here is, sorry, this is N, here is some M, and this is the image of M inside this N. And the meaning of this condition is that this image of N inside N is nice there, yes? And what is nice in this sense, that there are no some pathological for this, in this concept, things like that. There's some cusps, and I don't know how to call it, everything. So an example that let's have a circle as this N, and R2 as N. So this is our M, this is our N. So we can map this circle inside R2 to become like that. Yes, as we usually think that this is the circle, but circle as a manifold is something abstract that you have some charts and upclass and so on. Some set, topological space with charts and upclass. This is the circle as a manifold. So also this picture is very, very symbolic. Now you can map this circle inside the plane, and you see it so-called, yes? We see this image of this circle. And now we see that it is nice. There are no this phenomena there. But you can have also another mapping to the same manifold. When you see corners. This square inside the plane is also a smooth manifold, but this mapping is not immersion because they are corners. Yes? So if you find some coordinate expression of this mapping, that's some phi to xy, x and y as functions of phi, so you can, in principle, construct this square as by some coordinates. But then, if you compute this Jacobi matrix, it should be not nice in this point, not maximum rank. But here it will be nice. Yes. And embedding is immersion, plus there are no self-intersections. So for example, another example, say phi 3 or f3, again to the plane, you can map the circle to the plane in this way. Something like number 8 or infinity. There are no corners if you draw it properly, no cusps. So it could be an immersion, but it is not injective. You have self-interactions that some 2 points on this S1, on this circle, map to a single point in the plane. Yes? So here should be this and plus no intersections. So it is injective. There is a big theory about all these details of mappings. We will practically do not use them at all. We do not need them. That's why I do it in such very perfunctory way. Just to inform you that there is something like immersion, and embedding is quite important to understand, at least on this practical level, that because we meet quite often embedded manifolds, which are inside bigger manifolds. So what is embedding manifold? That you have an embedding of one manifold to another manifold. This is embedding. Then this guy, this Fm, is a submanifold, which means that it is embedded, one manifold embedded to another manifold. Yes, so submanifold is more complicated thing like subset with a manifold structure. It should be also nicely placed in this bigger manifold. Now, if you have a look to the official definition, real definition of manifold, it's rather complicated. It starts with that it is a topological space, Hausdorff, and I don't know what. Have a look somewhere. Well, also more or less in my book, but have a look to some finer books. That what is a definition of manifold, and it is so abstract that you don't need what exactly can be a manifold and what cannot be. So for those people who are afraid that from this definition comes something dangerous and not as we think, there is a theorem of Whitney. It was really an important theorem when it was proved that Whitney, there are several versions of Whitney theorem, and one of them is in my book. It says something like that each manifold is diffeomorphic to a submanifold of R to n plus 1, and here is each even C1 manifold. C1, we defined only C infinity manifold, smooth manifold. But you can imagine CK or C1 manifold, which is called differentiable manifold. It is that on intersection of two charts, you have these coordinate transformations of class C1, not C infinity. Yes, but it is not important for us, once again. But you understand that if we have a manifold, 1, 2, and this famous picture, so this mapping coordinate transformation from those coordinates to those coordinates, there are some xi's primed as function of x. When we gave a definition, we told that this function should be smooth functions. It is C infinity. But in principle, we could define it by some C2 functions. Then it will be called C2 manifold. So C1 manifold is, well, much worse than C infinity manifold in this sense, yes? And Whitney proved that even this manifold is diffeomorphic to a submanifold of this manifold. So there is a lot of information in this theorem. It was hard theorem. For us, it is interesting, at least this end, and also this number, that C1 manifold of dimension n. So for example, if we have a sphere, S2, according to this theorem, there is a submanifold of R5, which is diffeomorphic to this manifold. That means that for each purpose it is equivalent. That you can work with this submanifold inside R5, and you actually work with this sphere. Yes. We know that it is too much 5, because we know that there is a nice picture inside R3. So this theorem guarantees 5, and we know that in practical sense, this can be done in R3. Yes? But the theorem is general. It is not for just sphere, for any two-dimensional C1 manifold. So this number is also interesting, that for n dimensions, you need just 2n plus 1 dimensions in Rn to make a picture of your manifold, so to speak, to have it there as a submanifold. So there are no other manifolds like submanifolds of Cartesian spaces, actually. This is the main value of this theorem, that anything more dangerous can come, like some submanifolds. That means that some nice surfaces inside Cartesian space. Because of that, surfaces in Cartesian space become very interesting, because they are all manifolds. So we should somehow study them a little bit. And what we should know about them is that how they can be defined, how they are usually treated. So there are two methods. So surfaces in R, say n, constraint first, and second, parametrization. Two main methods, and both of them are well known for us, actually. From physics, especially in particular from theoretical mechanics with me, yes? So you know both these methods from theoretical mechanics. What is the constraint method? For example first, that let's have a Cartesian space, x, y, z, and here is a pendulum of the length L. So we remember that the points where this M can be, if it is at the end of the pendulum, can be characterized in this way, that we put some function to be 0. That all points which satisfy these constraints are possible points of this this mass. If here, of course, is 0, 0, 0 point, yes? Because this is just a sphere of the radius L. Well, when it is a planar pendulum, so it is so-called spherical pendulum. Now, if it is planar pendulum, it just can move in one plane. Let this plane be y equals 0, so xz plane. So we have now this, but also another one, with this function. So if you make 0 of this function and this function, from this you are on the sphere, here, two-dimensional sphere, plus phi 2 is the equation of the plane, y equals 0. So altogether you are on the circle, yes? Intersection of this sphere and this plane. So this method is well known for us. Well, it is also official method of one method of constructing manifolds. How it works, that you have some starting manifold with coordinates, say Rn, with x1, xn, and you have several functions which you put to 0. And if now some Jacobian of phi a with respect to xi if it has constant rank, there is a condition, it is case of some rank, constant rank. Say L, then there is a theorem that you obtain a manifold as those points x inside this Rn which satisfy these constraints as manifold of dimension n minus this rank. In most cases, one tries to find this constraint in such a way that this is not only constant but maximum rank, and that in this case these constraints are called that they are independent. Independent constraint means that this rank is maximum. And then you see that there is a simple rule of thumb that how to come to the resulting dimension, that the original dimension minus the number of constraints is the resulting constraint. But it is not always so, because if you have a rank which is not maximum, that it is not so. It is just a total number of dimensions minus the rank. So how can be retold this? That we can construct from this stuff a mapping of this Rn to another R, where phi's are coordinates, Rn with coordinates x's, x1 from xn. And we can construct from these phi's another R, Rk, with coordinates phi's, phi1, phi k. And now you have this Rn, symbolically Rk, this is the mapping. And where is our manifold? There are points axis which make this phase 0. That means that it is pre-image of this point. That all points here which map here. Here is the manifold. So it sits inside this first Rn, and there are points which map to the 0 point of the second Rk, because we put it 0. Yes. So this Jacobi matrix is a matrix of this mapping, and you find the pre-image of this 0 point and compute the rank of the Jacobian here and test whether it is constant in all points or not. So this is the general method of construct a manifold in terms of constraints. It can be shown by some theorem that there are manifolds which cannot be constructed in this way, that not all manifolds can be constructed using constraints, because there is a theorem, once again, I will not prove it, that whenever you do a manifold, construct manifold in this way, by way of number 1, your manifold is orientable. It is some point, some concept, which will be treated next year on mathematical physics number 2. What is orientability of manifolds? It is something which not all manifolds are orientable, of course, otherwise this concept should be avoided, but some manifolds are not orientable, and those manifolds cannot be constructed in this way, because it can be proved that anything constructed in this way is orientable. But there is another way, parametrization, and all manifolds can be constructed by parametrization. So what is it? We know it also. We maybe remember that when we in theoretical mechanics formulated this constraints in this way. Constraints, okay. That was a picture like that at those times in theoretical mechanics. That here was our configuration space given by those constraints. This R with arrow, other arrow is the sum of all R's with standard arrow. So the set of three-dimensional vectors altogether produces an R or three n-dimensional vector of some Rn, and the constraints are functions of these arguments when when you put to 0 you obtain some subset at least, but by this theory it is a submanifold. If this Jacobi matrix is okay there. We didn't speak about this Jacobi matrix in second year, just now. And you remember that in this language we derived some dynamical law instead of Newtonian mechanics, which was called D'Alembert-Lagrange law. And from that we obtained another law which was Lagrangian equations of second order. And what was the first step in going from D'Alembert-Lagrange to Lagrange equations? That we so-called solved these equations. That means that we wrote them in this parametric way, that you can parametrize these points here through some independent coordinates called Q, which are in theoretical mechanics called generalized coordinates. because of some historical reasons. So this is given by constraints, and this is given by parametrization. So what is in general parametrization? That your x's are functions of some other coordinates. In the book, the number of these other coordinates is what? Where is it? This number is m. Yes, and this is from 1 to n. This is from 1 to m, as we see. And this should be less than n. So the number of so-called parameters, these u's, should be smaller than the number of the x's. So once again, we can see it in this way, that here is Rm with u's. Here is some R, say n, with x's, small n. And now, either the whole space Rm or its parts typically is mapped here, and here is, let's say, this some phi. So this is phi of, say, this Rm. Sometimes just part of it. Maybe that just subset. So the manifold in this picture occurs here on the second Rm, not on the left one, on the right. Yes, inside the right. A well-known example, for example, this pendulum. We already wrote two equations for the planar pendulum just 5 minutes ago, some phi 1 and phi 2. And the solving of these equations, by solving, we can write, for example, R as a function of u, which is xu, yu, and zu. Here it is 0 because the constraint was that y is 0. And here it is L, here cosine of u, here sine of u, and here is minus. So this is parametrization by parameter just one, u. We have only u1 here. And this is the explicit formula how to express 3 coordinates in terms of less than 3, namely 1 coordinate here. And also remember that we can do it for the spherical pendulum. Theta phi are some coordinates on the sphere. And we can again express it, the spherical pendulum, by explicit formulas, which are L, which is each guy, and here is minus cosine theta, here is sine theta, cosine phi, sine phi. So again, we parameterize sphere inside R3 here by 2 parameters, which are called theta phi, usual spherical coordinates on the sphere. So, of course, there are a lot of examples of this type, but just those simple, I just remember that we did it sometimes already. And in the book, for example, you have an explicit parametrization, which looks like that we have x, y, z, w. So it is from R4 as functions, of some u1, u2, so explicit four formulas, which gives you first torus. Well, it's quite simple. Three-dimensional torus inside, two-dimensional torus inside R3 or R4. It is not a problem. But then also there is Klein-Bottle, which is a little bit strange manifold. And interesting thing about this manifold is that it is not orientable. And it cannot, because it is two-dimensional, it is guaranteed to be nicely placed by Whitney theorem in R5. Here, from this formula, you can check that it is nicely put in R4. So Klein-Bottle can be, by some formulas, placed in R4 nicely, without intersections, because what is famous about Klein-Bottle, you can check on internet, put Klein-Bottle, that it cannot be nicely realized in our world, in R3. There are some intersections necessarily. But in R4, it is already possible, without intersections and without these cusps and so on. So this is embedding of the Klein-Bottle into R4, given by this formula. It is an exercise, possible exercise for recitations to prove it, that this formula gives you Klein-Bottle inside R4. Of course, then you should define somehow Klein-Bottle in another way, in order to prove it that it is really Klein-Bottle. And you can also have coordinate expression or this parametrization for Möbius strip, for example, which is a well-known example of non-orientable manifold. It is known from popular literature on mathematics that there exists something like Möbius strip with also strange properties. The main strange property that it is not orientable, and you can have a nice formula to put it already in R3. It is not so problem because you can construct it from a sheet of paper. So these are these two methods of constructing manifolds, and there is also one special case which is called hypersurface. Important special case. It is given by one constraint, a single constraint. That means that its dimension is the original dimension in M, which has dimension M. The resulting dimension of the manifold will be M minus 1, or codimension 1, it is also called. So, for example, standard two-dimensional sphere inside R3 is a hypersurface because it is two-dimensional sitting inside a three-dimensional space. And of course, there are some special properties of hypersurfaces when you have just one-dimensional to the full dimension of the manifold. So they deserve some special attention. And just have a look at how you could test this condition on constraints, this Jacobian. If you have something like that, how this Jacobian looks like, what kind of matrix, what's the type of matrix it is, how much times how much. In general, Jacobi matrix is something like that. Now, what are these numbers here for hypersurfaces? Yes. So here is 1 and here is m. But matrices 1 times m are rather special matrices. They are just not columns but rows. Yes, there is 1 row. And what does it mean that it has maximum rank if it is just 1 row? How much is this rank and how you test that some concrete row has maximum rank? Sorry? It is non-zero, yes? So the only possible ranks of matrix 1 cross n are 0 or 1. Yes? Now, rank 1 means that there is just one linearly independent vector there. Yes? But linearly independence is not concerned when it is 0 vector. 0 vector is not linearly independent with some other vectors, yes? So it should be non-zero. So non-zero, any non-zero vector as a Jacobi matrix now gives you satisfying this constraint condition with Jacobian, yes? So for example, where is our constraint? It is already not here. S2 in R3, phi x, y, z equals sum of squares minus L squared. This is the function. So what is Jacobi matrix? It is phi over x, phi over y, and phi over z. That means 2 times x, y, z. Now, is this a 0 row or not? Where? Here. So if you know that sum of squares is L squared, is it possible that this vector or this row is 0? Of course not, because the sum of squares of 3 zeros is 0, and now it should be L squared, non-zero number. Yes? So it is not 0 here. That's why we have one linearly independent vector there, and that's why rank of this matrix is just 1, and it is maximum. So by this constraint, if it is smooth, of course, which is because it is a polynomial, so it is smooth and it has maximum rank, that means we have a manifold defined by this constraint. We don't know what manifold, but we know that it is a manifold. What about ellipsoid? Well, put it a squared, b squared, c squared, and you will obtain ellipsoid. So here should be some 2x over x squared and so on. And you see that still the vector is good. So not only the sphere is good, but also ellipsoid is good. And quite an interesting example is the SLNR group. This is, we know it as a group. Yes? There are matrices with determinant equal to 1. They preserve volumes. Now we can take this matrix and we can make it from it a manifold easily by saying that this will be, all of these guys are coordinates. We have just one chart. Yes? They are global coordinates in this manifold. One chart for whole group. Now we can write in terms of this coordinate condition that determinant of A minus 1 equals 0 and take it as a constraint. Here are all A's, not only diagonal ones. Well. So it is some function defined on GLR and R. If you write this matrix without this constraint, it is GL and R, or even more, because without determinant, they are the manifold of all matrices n by n. Yes. Now inside it, we have something defined by this constraint. Matrices with determinant 1. Now, is this function a smooth function? What do you think? This function as function of all matrix elements. So is determinant a smooth function of matrix elements? And if so, why? Some reason for it.
PLs are just multiplied in different ways.
Yes, the determinant is some sum of products and so on. So it is what type of function? It's a polynomial. We met this for several times already, that polynomial is safe. And determinant is just the polynomial of matrix elements. So that's why this is smooth. And what about now the second step? What about the maximum rank? This is just one constraint. It is phi 1. So it is this case of the hypersurface. If there is a manifold, it is a hypersurface. So we should prove that this row of the length n square is non-zero at these points where determinant A is 1. Yes. Now, I will not say the argument for you if you don't know it, why it is non-zero, this row. Either think it is the best way, then have a look to the hint. And it is something which you know probably from linear algebra or by sure. There is some decomposition of determinants to some minors and so on. This is a way to prove that this cannot be composed from all zeros. So at least one element here is non-zero. So if it is so, it has maximum rank, it is smooth. That's why this is a manifold. It is a submanifold sitting inside at least this manifold, GL and R, or the manifold of all matrices. Yes? So for us, it is very important that it is a manifold. Okay, now two concepts important, and then after very simple concepts, we come to the definition of what is a Lie group, yes?
Just to clarify, by constraints, we only want constraints.
Yes. Well, they are non-holonomic constraints which are outside the scope here. Yes. Good question, thank you. If you know what is holonomic and non-holonomic constraint, we are speaking about holonomic constraints. So, two important concepts. If we have a manifold, what is a curve on manifold and a function on this manifold? Extremely important and extremely simple concepts. Well, I will start maybe with the function. Function is a mapping from M to R. smooth mapping. Smooth function is a smooth mapping from this manifold to this manifold. R is also a manifold. Yes? Also Rn. Rn is the simplest manifold. So maybe R is really the simplest manifold in the universe. So from our manifold M, which can be complicated, to very simple manifold R. This is by definition the function. Is it reasonable definition? What does it mean? Here is our M, here is our R, and each point goes to some number. This is a function. But now we have our M is a manifold, so we have local coordinates by definition. So we have this picture with local coordinates. This is a chart, local coordinates somewhere. And because this can be inverted, we have effective mapping here. Yes, it is phi to -1 composed with this f. Now, what is it? It is a mapping from Rn, which is also a manifold, to R, which is a manifold. And this mapping, actually, what is it? It is the same type of mapping like that, but from another manifolds. So this is a function on Rn, by definition. How is it called with respect to this f? It is coordinate presentation. So each f can be transformed somehow to its coordinate presentation, but with respect to all possible coordinates. So just one f gives you infinite number of coordinate presentations. The same f can be treated through one coordinate presentation, another coordinate presentation, because we have many possible local coordinates there. Yes. So in order, when you study this coordinate presentation, you are not studying directly this mapping, but just this coordinate presentation of this mapping. So this is an important difference to have in your mind, to differentiate between f itself and its coordinate presentation. The same f can have many coordinate presentations. And very similar it is with the curve on a manifold. It is the opposite story. That curve very often called by as gamma. So we have this R. Call this, usually we call this coordinate inside t, like time. It is quite useful. And here is the manifold. And the mapping from here, this gamma, what it does. To each point, to each t, you assign a point inside M. So altogether, this is gamma of this R, or some part. You can take some open set inside, typically. So just here, for example. So what we see, if we see something one-dimensional inside this M, and so it is a good idea to call it that this is a curve. Yes, good and intuitive. That okay, it is a curve. But important thing is that it is not only the set of these points, but the t is inside. So it is parametrized set of these points. It is something which we maybe some before called it parametrized curve. That when in differential geometry we say a curve, we always mean parametrized curve. So if you make reparametrization, you can have this, another R, make some diffeomorphism like sigma here from tau, express t in terms of tau, and then you can combine it. It is first sigma, then gamma. So it is a gamma as a function of sigma as a function of tau, and this is t, yes, altogether. So it is a different function in terms of differential geometry. It is characterized by the same set of points there, but it is a different function. So for example, imagine that you go by highway from Bratislava to Trnava, some 50 kilometers, and you start at 8 o'clock and you have some Ferrari. So you have some concrete curve. At time 8:00, I am here, and at time in Ferrari 10 minutes or how many it is, I am in Trnava. Yes, it is one curve. Then sit to Trabant at the same time at 8:00. You will be later then, maybe. In a good Trabant, maybe not, but standard Trabant, yes. They are two different curves, but the paths are the same. All of them are going to along the same point, yes, here. So you have to differentiate that. Once again, curve is including this parametrization. Now, the same story like here, that we have coordinates. So once again, from R gamma to M, but we have some chart. So by composition, we obtain first gamma and then phi, this chart. So what do we obtain? Here we saw some curve, the image of this gamma, but phi makes from it first this guy and the image phi of gamma t. And what is it? By definition, it is a curve in Rn. This arrow is a curve in Rn. How is it called? Coordinate presentation. So it is coordinate presentation with respect to some particular coordinate system, local coordinates there. And again, clearly, if you change coordinates, the same curve will look differently because we see different coordinate presentation of the same curve. Some standard example, we have coordinates x, y, and we make a mapping which will be, say, cosine t and sine t. So what is it? Here is xy. And we go around the circle. Now, in coordinates r, phi, in polar coordinates, this is in Cartesian coordinates. In polar coordinates, we have r phi, and we have a mapping t goes to r0 and t. Yes. R as a function of t is a constant, some R0. And t and phi as a function of t is just t. So what we will see, the same curve in the picture, but sorry. Now we should write this r and phi plane. Yes, and we have constant r, but this goes something like that, hopefully. Yes. So they don't look like the same picture, but they are related to the same curve. This is coordinate presentation in xy plane, and this is coordinate presentation in r phi plane. Okay, and we are now prepared. I will have a look to the syllabus. What is a manifold? Mapping of manifolds, description of smooth surfaces. I hope that explained it. A manifold defined implicitly, that is also terminology, defined implicitly, it is via constraints. Yes, when you have constraints, it is called that we describe the manifold implicitly. And parametrically, we know a curve and a function on M and their coordinate presentations, it was now. And now this is the concept of Lie group. So now we are going to important definition that what is it, a Lie group? So a Lie group is now quite simple object, at least the definition is simple. It is a group plus a manifold. I mean that at the same time, or at the same object. It is something which is at the same time a group. We know what is a group already. And we know already what is a manifold. So Lie group is at the same time a group, which is a concept from algebra, and a manifold is concept from some differential topology or differential geometry. It depends. So in the same object, we have these two sides, but they have to be friends, these two structures. So there are two structures. And they should be compatible. Now, how to express the compatibility of these two structures? Well, it's a good idea to express these algebraic properties of the group in terms of some maps, because maps, smooth maps, are typical for our manifold picture. So, for example, what can be done with two objects in a group? You can multiply them. Now, you can look at this as a mapping. This mapping is usually called M because of multiplication. This nothing here inside is the group operation. Yes, typically it is notated in the way that GH, it is product in group. And where from it goes, so it is from where? It is from G cross G to G. Elements of G cross G are ordered pairs by definition. It is Cartesian product. Yet, yes, in explaining just a group structure, take Cartesian products of two groups. That means take elements G, H. This is an element of the Cartesian product, and map this pair to the group itself, how to do it? Use your multiplication. So by saying that what are properties of M, you can define this product. Yes, your product is nothing but a mapping from G cross G to G again. But if you want to describe its properties, you have to introduce another product, say I, G, by definition G to minus 1. It is inverse. Where it goes, this I from G to G. Take any element and define the inverse by this mapping. And also, the existence of unit element can be defined from G to G or some one-point set to G. It can be done at least in two ways. This unit element is usually defined like this. This is PT is a point. It is the smallest manifold. It's just 1 point, zero-dimensional manifold. And how it works, this? Well, this point goes to the E from G. By the image of this mapping, the point is mapped again to a point in the group, and you choose it in this way that it is mapped to the unit element of the group. Yes. So once again, it can be described by a mapping. That the image of your point goes to unit element. This mapping take inverse. Yes, and this mapping make a product. Now, what does it mean that this is just algebra still? It is there is no manifold inside this definition, and how to put their manifold? Just to say that these mappings are smooth. So first of all, that G is a manifold. Yes. Manifold. When you want to say what is a Lie group, it should be a manifold first. And second, that these maps are smooth. And remember that here it is just Cartesian product of sects, but we also introduced what is a Cartesian product of manifolds. So here it is already treated now that when we want to correctly formalize number 2, this should be already a manifold, and manifold G cross G. So I hope that it is a simple definition that how to make something which is at the same time a manifold, at the same time a group, and it is the two structures are compatible. Express the properties of the group as a group in terms of mappings, and then demand that these mappings should be C-infinity, that should be smooth. Yes? And this is the compatibility of the structure of the smoothness and manifold with the structure of groups, which is multiplication, making, inverse, and unit element. Now, we have some number of groups which we yet do not know whether they are smooth Lie groups or not. Some matrix groups from some lectures before. For example, GL and R. So we want to test whether GL and R is a Lie group or not. In order to do that, we should just study these 2 points. First, is it a manifold? Well, what is GL and R? Once again, they are matrices. 1, 1, 1, n, n1, nn, with determinant not 0. Yes. Now, without determinant, take this as coordinates. local coordinates. They are, then have a look and you see, oh, they are global. So what is here important? That think over this example. If we have R, X, this X can be taken as coordinate. Yes, so here we have point with X coordinate equal to something. Now take a manifold R without an origin, the origin. So put away this point. Think it over that if you take, there are two different things. One is complete R, one is R without a single point, say 0. Then have a look to the definition of manifold and check that this is of course a manifold, this complete, but also this incomplete, when you expel one point, it is also a nice manifold. This is the first thing to think. The second, that check that this X is a good coordinate again on both manifolds. This is important, that X is good also here. So if you put away some points from the whole R, you still can use this X as a local coordinate. Yes? Think it over from the definitions. This is the simplest example to think this idea. That if you have something and put away some subset, and you have some coordinates on the big picture, you can use these coordinates as good local coordinates also for these points which are good in the second case. And now the same idea here, that GL and R has no all A's. Yes, there are some A's which are not good because the A's which give you 0 determinant now are not good, something like this point. But it doesn't mean that you cannot use these A's as local coordinates on the set which remains, on the GL and R. Yes, so if this is hard to think, then think first this, and this then you see that, okay, here, also here, we can use these as local coordinates already in this smaller set. Here, they are of course coordinates on Rn squared, all matrices. All matrices are more or less Rn squared. But GL and R is not complete Rn squared, is Rn squared minus some points which are not there because of the determinant condition. But still these A's are good coordinates. That means we have an atlas. They are global coordinates, like here this X. Then, what about the second point? Say this M. How this M on A and B looks like? Well, let AB, the product of AB be some C. Then we know that CAB is AAC BCB. It is well-known formula for matrix multiplication. So take it as a coordinate presentation of some mapping. We have a mapping GL and R cross GL and R to GL and R. And in coordinates, it looks like that. It is coordinate presentation of M function in GL and R. It is coordinates presentation. In our coordinates chosen like that. And the only question is that, is it smooth? Well, what kind of function is this? C as a function of AB, again polynomial. It is second order polynomial, nothing more. So C infinity. So this mapping is smooth. It is okay. So this mapping is okay. The second mapping is, well, A to minus 1. Let's call it D. So once again, the official formula for inverse matrix, D as a function of A, is something, you know, some formula. Yes, it is what is some minor over the determinant, you remember. That you can, AB element, dA, AB is some minor AB over determinant of A. Plus, minus, maybe. It depends what you call the minor, yes? Now, is it okay or it has some problems, this formula? Is it smooth formula or not? And if yes, again, why? What kind of function is this minor? What kind of function is this determinant? Polynomials. This minors is degree 1 less than this determinant, yes? Because minor is also a determinant when you cross away something. So it is, the determinant is nth order polynomial, minor is nth minus 1 order polynomial. Now they are divided, and two smooth functions divided are again smooth functions when the denominator is okay. Yes, and it is okay because we are interested only on determinant which is y, which is non-zero. Sorry. Yes. So by this argumentation, you see that the inverse, the coordinate presentation of this mapping I, which whose content is inverse function in the group, is smooth. So altogether, we just learned that this is our first example of a Lie group. Or just think of group G given by matrices like that. So 1, 1, 1, 0, 0, 0. They are called upper triangular matrices. And, well, we see from it that they are described by coordinates x, y, z. There is an exercise that what is the m function, that multiplication of the element given by this and the element given by this. So here should be, once again, a triple at the end, if it is true that the product of such matrices leads again to such matrix. You can check that it is the case, that these triangular matrices multiply within the group. Yes, so you can compute it very easily. It will be 3 functions, and each of them of 6 variables. Yes? Here you have some u, v, w, say, So the first guy here is a function of x, y, z, a, b, c. And so the case for the rest. 3 dots, easily computed. And after computation, we should check that is it C infinity for formula or not, this U, V, C infinity or not, and so on. If yes, first of all, they are coordinates. Second, M is good. Of course, try to check also this I, that it is good. And if the answer is positive to all questions, then you say that this is a Lie group. Yes. It is a subgroup of Lie group of all matrices, this GL3R. On GL3R, we have, as we see, 9 coordinates. And on these subgroups, it is enough to have 3 coordinates. This is also called, by the way, Heisenberg group, because of some reasons. We will see when we will study Lie algebras that how Lie algebra of these groups looks like. And if you know something about Heisenberg relations and commutation relations in quantum mechanics, then you will see that it is connected with this. So either upper triangular group or Heisenberg group. Heisenberg didn't invent it, this as a group, but because of these Lie algebra properties, it is called like that. I think that it is everything which I wanted to explain on the lecture, and all other things can be done on the recitations. So yourself and tell to your schoolmates on the blackboard, on the green board, yes? So do you have some questions? It is week number 3, the concept of a manifold. And the next week is already Lie algebra, so I want to go to Lie algebras. That's why I just want to ask whether you want to ask something to this week with the concept of the manifold. No questions to this week? Okay, so now I go to further to another concept which has nothing to do directly with manifolds. This manifold was some exception, and we will go on with linear algebra, more or less, and it will be the concept of Lie algebras. And the way how I will explain it is that first we introduce the concept of Lie algebra by definition. Then we will see that we already know some Lie algebras, actually. Yes. And after that, maybe already not today, but on Wednesday, we will find that from each matrix Lie group, you can compute some Lie algebra. That if you have a Lie group, for us only matrix Lie group, but it is a general for any Lie group, then we can assign a Lie algebra. That means to compute a unique Lie algebra for given Lie group. Yes, there is a simple method to do it for matrix Lie groups. So in order to understand it, we just first want to know what is a Lie group by definition. And when we compute this something from Lie groups, we will see that, okay, this is true, this is a Lie algebra. And why it is important? Because Lie algebra is Lie algebras are part of linear algebra. And linear algebra is always simpler than to work with manifolds. Yes? So the working with Lie groups is working with manifolds. Working with Lie algebras of Lie groups is working in linear algebra. And if it is a lot of information in Lie group, sufficiently lot, it makes sense to compute first Lie algebra of the Lie group, to work with it, to learn a lot, and only for some very complicated things to go directly to Lie group. This is the strategy, that it turns out, really, that Lie algebra carries a lot of important information about Lie groups, and that's why we should learn as much as possible in the basics level, of course, about Lie algebras when we want to work with Lie groups. Yes? So what is a Lie algebra? It is a linear space, with, it is the first point, then there is a bilinear I will call it product that two elements go to something which is denoted like that, and it is from this L. So it is a bilinear product L cross L to L. It is not a bilinear form, because bilinear form is to R here, yes? Give me two vectors and I will give you a number by bilinear form. But here it is, give me two vectors, I will give you a third vector. It is some kind of multiplication. But this multiplication is not denoted by AB here, but like that. And this bilinear product, this kind of multiplication, has several properties. That it is skew symmetric, so if you do the product in the order AB, you give something, you obtain something in L. If you do it in the order BA, of course, you also obtain something in L, but this something is minus this first something. Then it is bilinear, so this is A1 plus lambda A2 B. So this property, it is A1 B plus lambda A2 B, and the same the second slot as for B. And the third property of this product is something mysterious at the level of definition, that Y, but it has some sense, that if you do product of AB, you obtain the third element in the Lie algebra. Then you can do the product with respect to C. Still, it is an iterated product. It is still an element in L. And now do the same thing with cyclic transformation that go with C here and AB here. And once again, so B, C, A. So it is here a sum of three terms, that second and third is obtained by cyclic permutation of these three objects. By the way, the fourth cyclic permutation is the first one already, so it is not there. Yes, just the three, in principle, different results are there. And the definition is that for any three elements of the algebra, this should be always zero. Yes, this is important, that for any three elements. Of course, this is also true that for any two elements. And also here, any elements. Yes. So it is a linear space with some strange product with these strange properties. Now, can we imagine something which works like that? The first example is standard three-dimensional Euclidean space with so-called vector product. So two vectors are multiplied in a way which we know as a vector product. So first of all, is the vector product inside E3? Yes. Now, does it have this property? Does it have this property? So is it skew symmetric? We know that yes, because a long time ago, somebody taught us this concept, and it was one of the first things which we learned, that whenever you do A cross B and B cross S, it is minus the one guy with respect to the other. So this is true from the definition of the vector product, so-called. Then, is it bilinear? Well, you need to know something about vector product, and if you know enough, you know that it is bilinear. Yes, it depends. Of course, the proofs depend on what was your definition of vector product. But from any definition, complete definition of vector product, you can prove that it is bilinear. And does it satisfy this strange property that A cross B cross C plus cyclic is zero vector for any three inputs? The answer is yes, but it is not very well known. I don't know whether you know it from your knowledge about vector product. Usually it is not very much used, and that's why it is not very well known that it is true. But are we able to prove it somehow by our machinery which we know about vector products? Which machinery you think that should be suitable to proving anything you want? Which we already learned, namely that I taught you this machinery, or maybe not. Maybe Radko Böhm was the guy in the first year, yes. But for a long time, I was the first guy who taught it, because students didn't know it from the first year. So you know that we can compute the ith component of vector product in terms of Levi-Civita. So we can take this as a definition. There are also other possibilities to define it. But if you have this as a definition, you can compute what is I component of I cross B cross C. I. It is epsilon ijk. Now I cross B J and C K, but by the same definition, this is epsilon J K no, J L M A L B M. So all together, you should put it together. Now, if this is the first guy, then you can, in the same way, compute the second and the third one, put it together, and if you know to work with epsilons, you will see that it is really a zero. So, what is the result? That this vector space, together with this product, satisfies definition of the Lie algebra. It is a three-dimensional Lie algebra, which means that the carrying vector space is three-dimensional vector space. the dimension of Lie algebra is the dimension of the vector space. Yes? So this is the end for today. We will go to other Lie algebras and some stuff around it on Wednesday morning. Thank you.